all the participants all over the country from various states and Maharashtra, from various institutes, engineering colleges, polytechnic colleges, and all AICTE approved institutions. So I welcome on the behalf of Sri Siddheshwar Devasthan and Sri Siddheshwar Women's College of Engineering, from our management, from our principal, and all the organizing committee. Welcome, Dr. Mohseen. I would like
Thank
to
you, sir.
take the privilege to introduce today's resource person, a distinguished scholar and researcher in the field of nanomaterials and energy applications. Dr. Tamboli is currently a research professor at Korea Institute of Energy Technology, KENTECH, means Korea Institute of Energy Technology in South Korea, where he focuses on advancing energy technologies. Dr. Tamboli is impressive. His impressive academic journey includes a PhD in chemistry from Pune Ahilya Devi Holkar, Solapur University, Solapur, and the Center for Material for Electronics Technology, CMET, Pune, India. Prestigious postdoctoral fellowship including the Brain Korea BK21 fellowship at Yangnam University and a fellowship at Hanyang University, South Korea. With a prolific research record, Dr. Tamboli has authored over 80 international research papers, filed multiple patents, and delivered talks at international conferences in countries such as Germany, Sweden, and Japan. His outstanding contribution have earned him numerous awards, including recognition as Foreign Young Associate of Maharashtra Academy of Science. Dr. Tamboli is an active member of Korea Energy Society, KES, and the Korean Institute of Chemical Energy. His research interests include the development of nanomaterials for energy storage and conversion, focusing on applications in batteries, supercapacitors, and hydrogen production. Dr. Tamboli's dedication to innovation and his global contribution to energy research make him an inspiration. Please join me in welcoming Dr. Mohseen Tamboli. So we are very lucky to have such a young scientist with us, and he is ready to guide us. So thank you very much, Dr. Tamboli, for accepting our invitation. And I would like to request you to start his session and deliver your research uh, contribution in the field of this energy applications. Thank you, sir. Over to you, sir.
Thank you, sir, for such a nice introduction. So I'm going to share my presentation.
Yes, sir. It's visible. You can start, sir.
Okay. So good evening, everyone. First of all, I would like to thank Symbiosis Women's College for providing this platform to present our work as a part of AICTE ATAL faculty development programs. I would like to special thanks to Professor Avinash Patil sir for the kind invitations and for giving me the opportunity to share insights on the nanostructures material for energy applications. I am Dr. Mohseen Tamboli, currently working as a research professor at Korea Institute of Energy Technology. So my research focuses on the development of nanostructured materials for energy applications with especially emphasis on the large scale hydrogen productions through photoelectrochemical and electrochemical water splitting and advanced materials for battery and supercapacitor applications. So first, let's sir, my slides is moving, right? Hello.
Yes, sir, yes.
Yes. Okay. Okay. Thanks. So let's start from our institute, Korea Institute of Energy Technology. KENTECH is a first global university that is solely focused on the energy research and technology, which was established recently in 2021 in South Province in South Korea. This is the first international institute dedicated exclusively to work on energy science and technology. Because this is only first premier organization in the world. They will focus on only uh, energy related research with the cutting edge research technology and for especially for the smart grids and clean hydrogen productions and like related to battery. KENTECH is equipped with very like state of art research facilities, and this aim is to first aim is to like next 5 years. So KENTECH will be definitely in QS world ranking below the 100. This is our ongoing research activity. My research mainly focuses on the development of advanced materials for energy applications, particularly in the large scale hydrogen productions through photoelectrochemical and electrochemical water splittings. I have published over 80 international research papers in AICTE journals. We are actively working on two promising technology, that development of anode material for lithium ion battery. This technology is already under preparations. So in this technology we have already developed anode material which is scalable, and now as you know that in battery the graphite is used for a lithium ion battery. So they have some disadvantages. So we have developed a hard carbon as an anode material, which is quite good as compared to the commercially available graphite. And now our technology is under preparation. So the another one is that we have developed a photo anode material for large scale hydrogen production. This technology is under preparations. So our lab mostly focuses on the technology transfer related work. We are publishing papers and file the patents too, but main our motto is to transfer the technology. So recently we have published some good quality papers. You can see here with good impact factor, and currently we have two project which was sponsored by Korea Electric Power Corporations, South Korea. These projects these projects are the ongoing projects, and the budget of approximately 16 crores to one project is 16 crore and another is 6 crore. So that project aims to develop the cost effective and high efficiency anionic exchange membrane electrochemical water splitting technology, and the innovative green hydrogen production technology based on the photoelectrochemical water splitting. So this is the outline of my presentations. It includes an overview of our research and the advanced materials developed in our laboratory, uh, and their application with various domains such as lithium-ion battery, supercapacitor, and hydrogen productions. So I start from here. The importance of materials in chemistry in the electronics. Material chemistry plays a pro-vital role in advancing electronic devices by enabling the development of high performance materials with tailored properties. Material chemistry is actually a root of electronics. Root of electronic devices, and these devices are constructed using various materials. This slides highlights that the use of material chemistry in the field of electronics. actually material chemistry is really essential for the production of the electronics devices, because it helps create the materials and uh, and to make electronic component. These materials actually includes semiconductor, printed device, and display materials, battery, and supercapacitor. So this is our mainly focus of our research. Our focus is the development of electron materials for batteries, such as like lithium ion battery and sodium ion battery. Our goal is mainly that development of high efficiency, cost effective, and stable electron material. The another our research field is that the supercapacitor technology, the development of electrode materials for asymmetric and symmetric supercapacitors. So we have already fabricated a couple of fabricated devices based on our novel architecture materials. So I will going to explain next slides in the supercapacitor sections. Uh, then another third is the main our current emphasis that green hydrogen production by research on large scale hydrogen production through photoelectrothermal and electrothermal water splitting, which emphasis on the developing a novel material using modulation and simulation techniques also. So another one is that materials which are going to develop in our lab. We have developed several new generation materials for energy applications, such as uh, polymer composites, metal oxides, hybrid composites, and carbon-based material. Actually, polymer composites we have like tailored for high performance energy devices applications, which are lightweight and flexible component for batteries and supercapacitor, such as polyanion silver and polyanion MWCLNT, polyanion metal oxides, and polyanion bismuth ferrite. Those polymer composites we have developed and used for battery and supercapacitor. Also, we also developed some metal oxides in our laboratory, like ANiCO24, MnCO24, and um, uh, NiMnCO24, and lithium ion molybdate and sodium ion molybdate too. Those materials also we have used for all energy applications. At the same time, so we have developed a hybrid composites and carbon-based materials. All those materials we have developed, and we have published a couple of papers along with filed patents. So now I'm going to explain the applications of our materials. So lithium ion battery. So lithium ion battery, there are two types of lithium ion battery. The one is non-rechargeable, and another one is a rechargeable battery. So in the rechargeable battery, it is also known as secondary batteries. It is the main feature is that it can be charged and used as multiple times. In case of non-rechargeable battery, so it is a designed for a single use. It cannot be recharged. So in case of rechargeable battery, we can utilize as a reversible chemical reactions, and it is a higher initial cost but cost effective in the long run. But in case of non-rechargeable battery, it is a like lower initial cost but higher overall expenses for the prolonged use. So in the rechargeable batteries, we usually use in the rechargeable battery. So we use for that mobile phones. In our mobile phones also we are using that laptops, power tools, and electronic components. That another non-rechargeable battery we use for like uh, oil drinking and other instrumentations. So this is the slide. It's showing the button cell. Button cell is also known as a coin cell. It is a small type of devices used in the various electronic devices. It is a type of actually rechargeable type of battery, and designed in the shape of button cell or coin cell. We can say, and it is offering high energy density in the form of in the small form of factors. uh, it is a key feature is that it is a compatible, lightweight, it is a rechargeable, it is high energy density, it is wide voltage range, and we can use in different applications such as watches and like mobile devices also small, we can use those type of devices. So this is the pouch cell. Pouch cell are the type of rechargeable battery that we can, which is a flexible, lightweight, and it is like sealed with pouch casting instead of rigid metal casting actually. So these cells are known for the high energy density and are widely used in the modern energy storage systems. So it is also have key features, and it is a flexible and lightweight. This power cell actually designed with the uh, allow for the flexibility, because we need recently it is also showing that uh, flexible mobiles, like folding mobiles or some watches, we need some flexible devices. So pouch cell type of devices we can use for the flexible devices, because this is high energy density and high efficiency for uh, to actually charge, to store the more charge. It is actually very safe uh, uh, as compared to the non rechargeable battery. So we can use these devices for electric vehicles actually, because now currently we need to think about to instead of using for the fossil fuels, so we need to use for some alternative. So electrical vehicles, we will use our devices as a battery, because it is a portable actually, and we can like variable devices. So as I mentioned, this is many advantages. It is lightweight and efficient for various applications. So this is the lithium ion battery work that way I did during my PhD. And generally lithium ion battery means lithium ion battery is actually type of rechargeable battery. The chemical energy which can convert it into electrical energy. So this is actually high energy density, and generally as compared to supercapacitor, we need more time for charging, and we also get a more time for discharging also. So mainly you can see the picture here. This is a coin cell and pouch cell. We have developed in our laboratory previously at CIMET Pune during my doctoral course, and that time we have compared those results with the commercially available graphite. That graphite is the commercially available material that using for the all electronic components and commercially available batteries. So we have developed a hard carbon material which is quite competitive as compared to that commercially available graphite. So we have filed the patent, and we have as compared to that um, uh, graphite, uh, as compared to our graphite, our hard carbon, it's showing the high specific capacity, and it is more effective as compared to the graphite, the which the specific capacity is over 400 milliampere per hour. So we used the natural sources for development of spherical hard carbon for anode material for lithium ion battery. As we know that the graphite is considered as one of the ideal candidate for lithium ion battery, but it's due to high stability and low like uh, wide range of availability. We need to think about the alternative material for graphite. So here we have developed nickel cobalt oxides behave for hybrid structures for as an anode material for lithium ion battery. So we have synthesized the nickel cobalt oxides behave for heterostructures by using hydrothermal methods. So in that case, first we have synthesized the nickel cobalt oxides by using a nickel and cobalt precursor, and we have prepared the nickel cobalt oxide nanowires. Then the nickel cobalt oxide nanowires we have uh, added in the bismuth vanadate precursors by using bismuth nitrate and ammonium metallate with different ratios such as 10%, 20%, 30%, and 40%. And we have prepared the bismuth NiCO2 bismuth vanadate composites. So you can see the results of nickel cobalt oxides behave for hybrid data structures. XRD figure demonstrate that the comparative that the XRD patterns of the observed data structures, uh, as as you can see in the figure in the XRD pattern, uh, there is different composition of BiO4 and NiCO2 composites. So 10% NiCO2 and BiO4 sample shows the peak here, the corresponding to the BiO4 phase. Most of the peak here is BiO4 peaks due to the very less concentration of NiCO2. But if you can see the 40%, it's showing the one hump is there. It's showing that the NiCO2 is present on the composites. Uh, the after that. After that, you can see the FECM images of BiO4 NiCO2 composites. You can see the figure A. Figure is A and B. It's showing the 10% BiO4 NiCO2 for composites. With actually with BiO4, it's showing the dendrite-like structures, and NiCO2 for showing the uh, uh, nanowire-like structure. So nanowire structure is connected with the dendrite structure. You can see figure A and B and C. You can see the figure C and D. There is 20% BiO4 and NiCO2 for composites. Figure E and F shows 30% BiO4 and NiCO2 for composites. And figure G and H, it's showing that the 40% NiCO2 and BiO4 composites. So here you can see the increase the concentration of the NiCO2 into BiO4, the the size of nanowires are reduced, maybe due to the higher concentration of NiCO2. But if you can see the figure C and F, it's showing that the uniform distribution of nanowires on the dendrite structures. And this is actually the optimized sample of our materials. So the 30% BiO4 NiCO4 samples we have analyzed by translation electron microscopy. So in that in that sample, we can also observe the same results with consistent with the FECM. You can see here the nanowires of NiCO2. It's connected with the dendrite like BiO4. So after that, we have studied the XPS. In the XPS spectral survey, it can be shows that all element of NiCO2 and BiO4s are present here, like such as the nickel, cobalt, oxygen, bismuth, and vanadium. All the elements are present here. After that, in the electrochemical study, the BN like bismuth, vanadate, nickel, cobalt oxide 30% sample shows highest surface area as compared to the bismuth, vanadate, NiCO2 for 10%, 20%, 40% electrodes. This is the BAT data you can see in the corner. Then, however, the actually the special structure of the surface area heterostructure, actually BN30 actually electrode demonstrating significant properties of electrochemical properties may be due to the higher surface area of the composites. Uh, in generally, if high the surface area, it can be develop more active sites, and if the more active site can be generated, then it increases the increases the catalytic activity. So after that, we like studied the galvanic charge discharge like studies in the lithium ion battery, and you can see the BN30 sample showing the high specific capacity as compared to the all other electrodes. In the case of cycling performance stability, we have checked, and you can see the stability BN30 sample showing the high stability and efficiency as compared to other electrode materials. After that, we check the materials with the different current densities. In the different current density also, you can see there is there is a BN30 sample showing the high specific capacity as compared to other BN electrode. You can see with the different current density like zero point 0.1, 0.2, 0.4, 0.6, 0.8. Or 0.20. So every current density BN30 electrode showing the high specific capacity. So So we have published the work on International Journal of Hydrogen Energy in Energy Research. Also, at the same time, we have demonstrated actually a novel material for the sodium ion molybdate. Uh, Actually, this sodium ion molybdate we report first time for this material for anode material for both sodium and lithium ion battery. Uh, we have synthesized this material by combustion solid state combustion methods by using a sodium ion molybdate precursors. And we have also studied this crystal structure by using density functional theory, and which is showing that this is a monoclinic phase with the specific group actually C2 by dash, and it is consistent with the XRD data. So after that, we studied the FECM analysis, FECM and TM analysis. We can found that this is cuboidal-like structure, and cuboidal-like structure having the size of 1 to 2 micron. Then we also studied. We also evaluate this electrode material for uh, uh, we also studied the XPS of this electrode, and we found that all the elements of nickel ion molybdate, such as sodium, iron, molybdenum, and oxygens, are present here. The oxidation state actually little crucial for development of this novel material. So the oxidation state of this element of sodium is sodium, iron, molybdate, and oxygens are sodium is plus 1, iron is plus 3, that molybdenum is plus 3, and oxygen is minus 2. Oxygen is 2, respectively. This is actually crucial part when we have developed the novel material, uh, novel electrode material for any applications. This actually synthesized material we have also again demonstrated for lithium ion battery and sodium ion battery. It in the lithium ion battery, it's showing also the excellent performance, which showing the 99% Coulombic efficiency even after 50 cycles in the different current density with 50 milliampere gram in milliampere gram. So, but when we compare those results with the sodium ion battery, even though sodium ion battery have a less specific capacity as compared to lithium ion battery, but that compared to the stability, the sodium ion in sodium ion battery, NiFeMO for electron material, it's showing the consistent good stability as compared for the lithium ion battery. So mostly because of the maybe due to the sodium content in the material. Again, that same kind of material we have developed iron LiFe lithium ion molybdate. This is also same kind of material which we previously developed with sodium ion molybdate. At the same time, we have observed the same type of morphology. We have just changed the lithium with instead of sodium, and we checked the detailed performance of the lithium ion battery. Even we have checked the those electrode material for sodium ion battery, but we did not get that much improvement as compared to the lithium ion battery, lithium ion molybdate. So you can see here the exact pattern of lithium ion molybdate. It's showing the same result we observe, the same like sodium ion molybdate. It's showing the pure. We observe that the monoclinic phase, which pure phase, we observe here in XRD. In case of SCM data, you can see here again cuboidal like morphology we observe here. And after that, we again analyzed by TM. The, the TM results are well agreement with the XRD, well agreement with the SCM data, and it's showing that the cuboidal like structure. Also, in the XPS also showing the same results, same consistent results. It's showing the oxidation state are well which match with the material which we have developed, and all the elements are present here like lithium, iron, molybdenum, oxygen. So after furthermore, we have studied this material for uh, lithium ion battery, and when we check the charge discharge capacity, we have first and second initial cycle. It's showing the high specific capacity. almost more around 1100 and 926 milliampere hour gram. It's showing the almost threefold more than the commercially available graphite. When we check the stability of our material after even 25 or 50 cycle, it's showing the same consistent results and having good stability of this material as compared to the sodium ion molybdate lithium ion battery results. But if you can see the figure C, it's showing the different current density. We have checked our material with the different current density, and we have also it is showing also the same consistent results with the different current density. It's showing the high specific capacity. After that, we have demonstrated, we have synthesized the nickel substituted manganese cobalt oxide materials for anode material for lithium ion battery. We have synthesized this material by hydrothermal method. Uh, you can see the morphological feature it's showing in the SCM results. In the case of SCM, it is actually really see the beauty of our work. In that case, actually, we observed that the three-dimensional material is converted to the one-dimensional material. Actually, it is interesting part that how the three-dimensional material can transport in the one dimensional material. uh, Actually, in case of there is some uh, parameter about the wire addition of nickel into Mn. Actually, the pristine structure of manganese is actually body centered and nickel is face centered structure. So in the crystallographic structure, the face centered cubic structure, the face centered actually cubic structure of nickel have a tendency to grow the one dimensional wires as compared to Mn. So the body centered cubic structures are changed to the one dimensional. Therefore, actually, the incorporation into the nickel into Mn accelerate the one dimensional growth under a different hydrothermal condition. So the same results we observed in the TM also. There is a you can see the nanowires are. This is actually Ni substituted MnCO2 per sample. It's showing the porous structures for NiMnCO2 4. Uh, then we have check though this material for anode. We have checked this check this material for lithium ion battery. The nickel manganese cobalt oxide electrode exhibited outstanding electrochemical performance. That is, it is almost, you can see there is 90% capacity retention and almost 700 around 700 milliampere hour gram even after 2000 cycle. Uh, Even after 2 hours cycle, we observe that much good specific capacity. So importantly, it is actually high discharge capacity. You can see their high discharge capacity with different current density. Even you can see the as compared to the pure MnCO2 4, nickel substituted manganese cobalt oxide showing their high specific capacity as compared to uh, the pure MnCO2 4. Maybe there is also one reason that there is nickel manganese cobalt oxide. It's showing the wire showing the porous structure, and it is when it is a porous structures. It actually provides the access of electrolytes and lithium ion for effective electrochemical reactions. So it can be generated more active sites, and the catalytic activity can be improved. Then we have uh, this is actually battery results. So I'm going to explain about the comparison of battery and supercapacitor, because I'm going to explain the next work by supercapacitor. In the case of supercapacitor generally have high power density, and battery it's showing the low energy density. So battery store the energy chemically, and during charging and discharging chemical discharging of battery reaction, it occurs the uh, electrode in electrodes that surface chemical reactions. So in case of supercapacitor, it we can store the charge in electrostatically at the electrode and electrolyte interface. there is no chemical reactions observed, which allows to faster charging and discharging process actually. So the another factor is that energy density. Battery actually, as I mentioned, that it is a high energy density, but as compared to supercapacitor, it is low energy density as compared to the batteries, and it is more generally in the supercapacitor is showing the more suited for the short term energy busters or something. So in the case of power density, generally power density battery, it's a lower power density as compared to supercapacitor, and charging and discharging time. Battery it show it is slow charging and discharging process. In case of supercapacitor, it is extremely fast charging and discharging process. And the if you can compare those with the cycle life, so it is a battery, it's showing the limited cycle life, and we can say there is a battery limited cycle life showing 100 to a few thousand cycles we can do in the battery performance. And in case of supercapacitor, it is very large cycle life up to the million cycles, and there is minimum maybe until 1 or 2 million we can do the cycling of a battery. So battery, in case of battery, we can use the in electrical vehicles also. In the case of supercapacitor, we can use in the memory devices and other applications. So after that, here we have synthesized the same material, that nickel substitute manganese cobalt oxide. But in that case, here first we have developed this nickel substitute manganese cobalt oxide material. Those materials we have actually first tested for supercapacitor application. After that, we use the same material for battery application. So I'm going to explain the results, what our materials, how we synthesize the material, and how we have received the results. So you can see the experimental process. In the experimental process, we have first synthesized the manganese cobalt oxides by using a different manganese, cobalt, and urea as a precursor. In that MnCO2, we have added the different composition of nickel like 0.2, 0.4, 0.6, and 0.8, and pure MnCO2. So this is the experimental process we did. So this is the result and discussion part of our work. You can see the XRD figure, comparison XRD pattern of the uh, different electrode material like nickel cobalt oxide and manganese cobalt oxide. So in case of manganese cobalt oxide, MCO, we have given the label as MCO. When we are added the 20% or substituted 20% by nickel, we have given the label as 1, 40% 2, 60% 3, 80% 4, and pure NiCO2 4. So this is the XRD pattern, comparative XRD pattern of nickel manganese cobalt oxide sample with different ratio of nickel, different ratio of the nickel, and all the different diffraction peak actually can be indices in the cubic MnCO2 for spinel structures. There is a no impurity peak we have observed here. The observed here, and this extended pattern of all the samples with the different emulsive compound contains the when we can check the JCPD results, and it is a match very well with the MnCO2 per spinel structure. Then we have studied the surface morphology of our material. So in FECM, you can see figure A is showing the MnCO2 pore. In that, as I mentioned earlier, MnCO2 pore is showing the cube-like structures. So this is the figure A showing the MnCO2 pore. Figure B is showing the 20% nickel substituted by MnCO2 pore. Figure C is showing the 40% nickel into the MnCO2 pore, and figure D is showing the 60% nickel into MnCO2 pore, and figure E is showing the 80%, and this is pure NiCO2 pore. So you can see the beauty here. When addition of the nickel into the MnCO2 pore, you can see the cube structure, how the three-dimensional material can be converted into the one-dimensional material. So after addition of the 20%, the cubes are demolished and going for the starting the material to growing for the one dimensional. So this is a figure is cubes, then 20%, 60%, 40%, and you can see the figure D is a 60% nickel substituted MnCO2. You can see the when the 60% nickel CO2 nickel into the MnCO2, it's showing the totally it's growing the one dimensional nanowires. uh, as I mentioned earlier, there is a crystallographic effect. This is the Mn is the body centered structures, and Ni is a spin like uh, cubic structure, one dimensional structure. So when we can incorporate the one incorporate nickel into MnCO2, there is a one dimensional growth can be happen, and it is the converted the material from three dimensional to the one dimensional. The after that you can see here the elemental mapping of our synthesized material. It's showing the all the elements are present here, that Mn, nickel, cobalt, and oxygen. In case of the Tm results, we have like you can see the Tm results is also showing the consistent results. uh, the figure A is showing the yeah, MnCO2 port. There is some cubes are showing like MCO sample is showing the uh, distorted small part of the cubes, and after that when we can add into the MnCO2 pore, it have a pore structure with the diameter of around 10 nanometer microsize, and the nanowires we have observed here. Then figure C is showing the NiCO2 per uh, nanostructures. But when we measure the surface area is showing the Ni 60% nickel into MnCO2 per, showing the high surface area as compared to the uh, like MnCO2 per and NiCO2 per. When we check you can see the high resolution images. Here it's showing there is a porous structure, and figure uh, E is showing the selected area electron diffraction pattern, and all the planes are very well matched with the XRD planes here. Then again the figure F in TM section, it's showing that the all element here. Then we have also studied those material uh, confirmation of the element, and uh, checking the oxidation state of our material. Then it is showing the all the elements are present here, such as nickel, cobalt, manganese, and oxygen. Then we have checked the electrochemical study. When we can check the electrochemical study, we have electrochemical study, and we have we have analyzed this study by using cyclic voltammetry, and we have measured the specific capacitance of the material. Uh, in the case of according to that cyclic voltammetry study, we found that the 60% nickel substituted into NiCO2 per sample, showing that the high specific capacity, such as more than 2000 farads per gram, as compared to the other substituted material, nickel substituted MnCO2 material. Then we again check this material. We again measure the specific capacitance by using charge discharge process, and we have also received the same results which we have received from cyclic voltammetry. The maximum specific capacity of 60% nickel substituted MnCO2 showing 1762 farads per gram, and as compared to the all other electrode, the 60% nickel substituted MnCO2 per sample showing the good performance and good electrochemical property. Then after that we have uh, check the asymmetric supercapacitor devices. So basically there are two type of asymmetrical supercapacitor device. There is a symmetrical supercapacitor and asymmetrical supercapacitor device. In that case we have check this material for asymmetric supercapacitor devices. In the case of asymmetric supercapacitors, we use our material as a one we as a one positive or negative electrode. But if we can do for the same material for symmetric supercapacitor, we have to use the same material for positive and negative electrode. So generally, in the case of positive electrode, when we are going to make a device here, a symmetric supercapacitor, we have used it as a carbon as an positive electrode, and our like optimized electrode, 60% nickel substituted NiCO2 MnCO2 for this electrode. We have used this optimized electrode for uh, positive negative electrode, and we have fabricated this asymmetric actual devices, and this actual devices which is also showing the high Faraday efficiency and high specific capacity as compared to that other reported literature. After that, we have synthesized conducting polymer carbon nanotube composites for supercapacitor applications. In that case, first we have actually commercially purchased the carbon nanotube, multi-walled carbon nanotube, and then multi-walled carbon nanotube we have functionalized the multi-walled carbon nanotube. The reason is that if we can functionalize, it can open the COH group, and it will be helpful for developing the more active sites. So in that case, we have functionalized this material, and after that, this material we have used for making a composite material with the conducting polymer. Generally, polyaniline, one of the promising and very cost-effective, stable conducting polymer as compared to the other conducting polymer, and we used this MWCNT and polyaniline for supercapacitor application. So when we can check the XRD results, it's showing that there is a the red color. It's showing that the polyaniline and carbon nanotube. It's showing that there is a no carbon peak observed in the XRD in polyaniline and carbon nanotube, because due to the overlapping of the carbon peak in the main peak in 25 degree, you can see here. So in the case of the thermal study, you can see the polyaniline MWCNT is showing a three-step decomposition process and showing that the good stable conducting polymer. And we have also checked this material for morphological aspects. In the case of morphology, we can observe that the 20 to 25 nanometer carbon nanotube, and when we can coat the non-carbon nanotube, the uh, size is improved because due to the coating of polyaniline to the carbon nanotube. In the case of we check the specific capacity of the polyaniline, and showing that pure polyaniline showing very less specific capacity, but as compared to the conducting, when we can make the composite with the polyaniline, it's showing the high specific capacity as compared to pure polyaniline. Then after that, we have again synthesized BI silver composite material for symmetric supercapacitor. In the symmetric capacitor, as I mentioned, that we use the same electrode for our both the side, like cathode and anode side, means positive and negative electrode. This actually is a novel material where that time we have first developed for symmetric supercapacitor, and this symmetric cell has been actually successful actually for fabricated for the first time, and it is actually demonstrating excellent supercapacitor properties. You can see the figure in the XRD pattern. There is a BI4 peak, but there is a less concentration of silver. We cannot see the exact peak, but when we can go for the EDS, it's showing the silver is present there. And you can see the FECM images. FECM images, it's showing that the dendrite-like structure of BI4. And when we can add the silver there, there is some agglomeration can be occurred here after addition of the silver. And when we can measure the elemental mapping also showing that all the elements are present here. So when after that we have studied the material for supercapacitor application. When we make the cell, actually these cells offer an extended voltage window, actually 1.6, which further leads for the excellent energy density for around 2.63 milliwatt hour centimeter cube, which is very high power density. Actually, also also this symmetric cell exhibit a significant high voltage capacity and good cycling stability. Almost it's showing the 82% retention capacity after even after 4,000 cycles. Again, we have also developed that reduced graphene oxide behavior for composites. Mostly we have used the behavior for material, because behavior we have used for both the applications such as battery, supercapacitor, as well as we have used the same material for hydrogen production also, because BF4 is one of the promising material due to their like due to their promising properties, such as it is a tunable band gap, and it is a very cost effective, and we can do the in scalable form also. So here we have developed a reduced graphene oxide BIO for composites for high energy density symmetric capacitor. At the same like a previous scheme, we instead of silver we have used reduced graphene oxides with the different content of reduced graphene oxide into BIO4, and we have optimized the one component for BIO4. So we have synthesized this material for hydrothermal method. You can see here in the ACM image is showing that uh, some RGO sheets are showing here in the hydrothermal, because due to the some when we can go for the higher loading of RGO, it is showing some small sheets observed in here in the FCM, but you can clearly see the dendrite like structure showing here, which is means that the BF4. When we going to go for the elemental mapping, it's showing the all the elements are present here, like bismuth, vanadium, oxygen, and carbon here. Then we can check this material for supercapacitor applications, and we have also received we also like considering this for the electrical property, we have also it is also shown that the good specific capacity material, capacitance material, and it is having almost more than 90% retention capacity of optimized reduced graphene oxide behavior for composites. So now I'm going to move to one another part. This is uh, uh, development of material for hydrogen productions. So this is an introduction to the hydrogen. Uh, Hydrogen is actually emerging as a key player for the uh, key player for the transportation purpose, because it is a very like a clean energy. Hydrogen is a clean energy systems. Uh, it is very like abundance, and it is a zero carbon emissions. Nowadays, as I mentioned earlier, that hydrogen is a need for our future life, because in the fossil fuels, in future the fossil fuels, we cannot depend the fossil fuels, because fossil fuels we can be end one of the day, then we need to for alternative. So now people are working on the battery, but again battery have some disadvantages, such as that again we need to for charge and discharge. So if we can do the charge and discharging process, so we are like it is a time consumable. After that the battery have some disadvantages. That one main part is that after battery capacity can be finished, after that where we can demolish the battery, or where we can throw the battery. So there is alternative as a hydrogen, because hydrogen is a fuel, and hydrogen is fuel, and we need this is like same like our like petrol and diesel. So this is one of the key player for our future lives. So today I'm going to explain about there is how we can produce the hydrogen by using the cheap and convenient method, because recently and currently we are producing the uh, hydrogen from fossil fuels also, but it also have some drawbacks, such as that it emits CO2 and carbon and more gases that will be effect on the uh, environment. So we need to choose the alternative of that hydrogen. So we are going to explain about the green hydrogen production. So green hydrogen production we can produce by electrochemical or photoelectrochemical water splitting. As I mentioned earlier, that the hydrogen is actually is gaining a global attention in the key solution of addressing passing energy and environmental challenges. Um, Hydrogen actually we can mainly use in for we have to produce the hydrogen with the zero emission energy. But as you know, you can see here, though we can there is different company byproduct. There is H2S, or suppose there is water is there 70% waters are available in the earth. So we can produce the hydrogen by using a natural sources, like such as water. So here I'm going to explain about the green hydrogen production from water, and also there is some byproduct from company. There is such as H2S. So or ammonia. In the case of H2S and ammonia, we can do some chemical reaction, and in the chemical reactions, we can produce the hydrogen in the system. So we can produce the hydrogen. It is a totally green hydrogen production. There is um, no carbon emission. There is there is a zero carbon emission, and there is no any byproduct. So currently we are using the green hydrogen production. We are used for fuel cell. The fuel cell is, you know, that the their byproduct is water. So water is there is no any effect for any environmental effect. But producing the green hydrogen is a challenging task, because green hydrogen production is one of the uh, key factor to make to produce the hydrogen. There is some such as now the green production of the green hydrogen production technology. It's a little bit costly as compared to the available hydrogen technology. So currently we are working on that topic. And green hydrogen production is actually becoming a central focus on the uh, global energy due to their environmental and economic benefits. So if we can use the fossil fuels, there is actually large amount of carbon dioxide or greenhouse can be and it can be like a effect on the global warming and climate change. So as I mentioned that we need to uh, we need to overcome this issue, and we have to produce the green hydrogen productions which are very clean and which are very cheap, which there is it should be not any byproduct. It should be like efficient. And um, now our main aim or motto is to develop this electrode material for green hydrogen technology. Current hydrogen actually generally hydrogen can be produced through different methods based on their energy sources and environmental impact. So you can see here, nowadays the hydrogen can be produced by using like different method, that biomass conversion or electricity by heat using by thermolysis or electrolysis by photocatalysis. But according to that, we have to produce. We have to our main is that the production of the uh, cheaper hydrogen production, which can be uh, uh, cheap as compared to the commercially available hydrogen production technology. Now I'm going to focus about the green hydrogen production technology. Among the methods of green hydrogen productions, now photovoltaics electrolysis is actually one of the method that produce a green hydrogen production, but still it is hindered by the high cost. But in case of the photocatalytic water splitting technology, there is one also alternative for green hydrogen production, but it also suffers from the low efficiency. So in this context, photoelectric water splitting is a advanced and promising method for producing green hydrogen production. which can we can utilize that solar energy that can split the water and oxygen. um, Actually, this photoelectrochemical water splitting, production of hydrogen production from photoelectrochemical water splitting, it is actually bridge between the photovoltaics and photovoltaics and photocatalytic water splitting. But still, the photoelectrochemical water splittings have some challenges, and specifically for efficiency and stability of the material and scalability. So current PEC system is like challenges in achieving high solar to hydrogen efficiency. High solar to hydrogen efficiency means how much hydrogen we are producing from that system, and we have measure the sunlight, how sunlight is coming, and according to the hydrogen, how much we have evaluating we are evaluating the hydrogen from that system. So solar to hydrogen efficiency is still challenges, and stability of the material also one of the important factor for producing the hydrogen. In the case of PEC, photoelectric water splitting, uh, photoelectric water splitting producing from this system is little bit like costly as compared to the other method, but it is a very like we can produce the hydrogen from a large scale. The photoelectric chemical water splitting technology, actually basically we can use the sunlight and water. Then actually also it is actually environmental safe. We can There is no byproduct in the photoelectric chemical system, and we can use for both the small scale and large scale when we can produce the hydrogen here. So here I'm going to explain about the principle and concept of the photoelectric water splitting. When sunlight is absorbed by the semiconductor material, it excites the electron. I'm uh, talking here about the principle. When the sunlight is absorbed by the semiconductor material, it excites the electrons in the valence state and the promote valence band, and promoting them to the conduction band. So when the electron goes from the valence band to the conduction band, and hole can be generated, and it is then hole can be generated, and then it split the water, and we can produce the hydrogen. This is the principle of the photoelectric water splitting. In the basically photoelectric water splitting, in the photoelectric water splitting, we generally, when we can compare the result with the photo catalysis and electrochemical water splitting. In case of PEC requires specified semiconductor material. That gap, like we have to choose only specific semiconductor material that can be matched with the vacuum band, to the vacuum band and valence band. So why specific semiconducting material? Because we need the specific energy to split the water. So we need the specific semiconducting material for photoelectric water splitting. So recently people are using different strategies to improve the photoelectric performance, that I will explain next slide. Here you can see our main motivation of the work. Photoelectric water splitting is, I mentioned that the promising and like very visible approach for generating hydrogen and oxygen. Uh, but now I'm going to focus about the single metal oxides. In the case of single metal oxides, as I mentioned, that the BiO4, BiO4, BiO4 is in BiO4 we will use for the hydrogen production for PEC water splitting. Generally, single metal oxides we have already previously reported that some single metal oxides have used for photoelectric water splitting. But in case of say single metal oxides such as TiO2, TiO2 has a like uh, very large band gap. So that it is like also only active in the UV region. So generally, photoelectric water splitting is showing when we can produce hydrogen by a visible um, range also. So again we have to do some modification. So single metal oxides, when we can use for the single metal oxides, again it can be have like some limitations, such as that the it is like only active in the UV region. AICTE I am talking about that. Then we have to do some like doping or using some co-catalyst or some surface modification. But we are using for the BIO4 as a one of the promising material due to their tunable band gap. It is a low cost and easy for preparation methods. So again, BIO4 have some limitations, such as it is a poor band gap, poor electrical conductivity. So that we in previous studies also we have used to make a different composite with BiO4. Because of that, one reason is that BiO4 have poor electrical conductivity. So our strategy is to make heterostructure material with by using another material, by using some dopant or using some two-dimensional material or some dopant also, or using a co-catalysis. So when actually the drawback of this BIO4 also, it is like showing the low efficiency. When we can make a composite, it's showing the improve light absorption and increase the conductivity. So our aim is to develop the photoanode material with high solar to hydrogen efficiency. When we can produce the material with the high solar to hydrogen efficiency, then we can produce the more hydrogen. Recently we have published this work in energy. So we have developed a BIO4 graphene molybdenum like heterostructure material for photolithium water splitting. In this in this paper, we have synthesized the molybdenum, graphene and BIO4 composites. So I'm going to explain here the synthesis of how we made the composite here, because we use the graphene, because graphene is one of the highly conducting material, and it is a two-dimensional material. When we can use the like graphene here, the electron can easily transfer from the one side to the another side, and when the electron transfer from one side to another side, and it's showing the high photocurrent. So first in the synthesis method, first in the we have used fluorine dope indium oxide FTO, and we have coated the graphene on the FTO. Then graphene we have coated a different layer, like one layer, one cycle, 3 cycle, 7 cycle, 5 cycle, 7 cycle, and 10 cycle. After that, we use the BiO4 and molybdenum precursor, because molybdenum is also one of the good dopant, because it is have a less ionic size as compared to bismuth, and some intrinsic doping. It's showing the high effect for the dopant. So in the case of molybdenum, we dope the 0.5, 1.5 and 2% to the BiO4, and this solution we have again coat on the graphene layer, and we have prepared the BiO4 graphene composites. Then we have checked the PEC performance. So here XRD pattern, you can see here the XRD pattern confirmed there is a crystal XRD pattern. You can see the XRD pattern for BiO4 graphene, and BiO4 molybdenum dope BiO4 graphene. In the case of XRD, you can see most of the all the peaks are in the all the peaks here only observe about the BiO4, because it is a very low concentration about the graphene, and very less concentration about molybdenum. But little shift is observed here in 100% peak in XRD here, but it's showing very less. So figure B is the Raman spectra of the photoanode material, BiO4 graphene, and molybdenum dope BiO4 graphene. So here you can see here figure C, after addition of the molybdenum, the peak can be the shift is observed here in the figure C. Uh, it is it is maybe due to the addition of the molybdenum. Then you can see the figure D. Figure D, it's showing figure D. It's showing the XP spectra of BiO4 and optimized BiO4 molybdenum graphene photoanode. the graphene therefore graphene molybdenum photoelectrode exhibit a similar peak like bismuth, vanadium, and oxygen spectra. Uh, Also, same we have the same peak we have observed in the behavior also, but when we can check the XPS, the shift can be observed here. In the here, you can see the BA4 and BA4 graphene and molybdenum. Some small shift is observed here in the lower side. It's showing that the molybdenum doping in the composites. So in the same type, we have same thing we have observed in the figure E. It's in the vanadium. It is also showing the peak little peak shift is observed here. In case of figure F also, there is a molybdenum, and figure C is figure G is a carbon. The we have used the carbon here, graphene here, so carbon is showing here. Then we have measure the FECM here. The surface morphology and microstructure of this all the photoanodes actually plays a crucial role for development of improving the photoelectron properties. Uh, Figure A, B, C, D, and E, F. There is a like SCM images. In case of figure A and B, this is a high magnification and low magnification images of BI4, and figure B and E, it's showing the uh, figure it's showing figure A and B is behavior for graphic. Figure D and E is the uh, thin film. Figure C and F is the cross sectional area of all this, both the electrode. Actually, you can see figure F. This is cross section of behavior for graphene and uh, for graphene and molybdenum, but we cannot see the graphene here, maybe due to there is a very less concentration of graphene, and we have used the graphene is very less quantity, and the graphene the sheet diameter is around 2 nanometer, so we cannot observe the graphene in the figure here. But we can see the figure C, there is a pure bismuth vanadate. So in case of figure A, there is no much dusty, no much changes observed here. But when we can go for the when we can go for the addition of the graphene and molybdenum in the figure D and E, figure and D and E, it's showing that the agglomeration can be occurred maybe due to the graphene and molybdenum. Then you can see the TM images of our optimized behavior for graphene and molybdenum. So figure A is the low magnification images. Figure B, it's showing there is graphene and behavior for structure you can observe here. We cannot see the molybdenum here because due to the we have doped up molybdenum. So in the case when in the dopant we cannot observe the molybdenum here. So you can see the figure D. It's showing that the lattice fringes are very well matched with the uh, bismuth vanadate structure, and figure E is the SED pattern. Figure E is the F is the electronic images that it's contain. You can see the figure G to I. It's showing that the all the element like bismuth, vanadium, oxygen, and carbon. In the case of XRD, you see you observe that there is a no carbon peak we observed here, but when we can check those results with by using a elemental mapping, the carbon is present here. Then those material we have tested for photoelectric performance. You can see the figure A. They we have measured the linear sweep multimetry of all the photoanode. There is a figure 8 showing the graphene layer. We graphene layer coat on the FTO with BAO4. There is different graphene layer like uh, 1, 3, 5, 7, and 10. And in that case, there is a three-layer graphene concentration is optimized graphene BAO4, and then we add their different molybdenum content like 0.1, 1.5, and 2. In that case, we can you can check here 0.5% molybdenum dope graphene BAO4. It's showing the highest um, photocurrent, means higher the photocurrents, we can produce the more hydrogen. In the case of figure C, figure C is showing the sulfide oxidation we did. Actually, we did we studied uh, both the studied like sulfide oxidation and sulfate oxidation. So sulfide oxidation generally used for favorable for electrical property because of the SO3H group. But in case of here also, we have observed the consistent results here after adding the BiO4 and molybdenum, after adding the graphene and molybdenum zero point 0.5, it's showing the highest photocurrent as compared to the pure bismuth vanadate and graphene BiO4. Again, we have studied the uh, we have checked the conductivity of material by using the Nyquist plot. In the Nyquist plot, you can see here the bismuth vanadate graphene, and molybdenum bismuth vanadate graphene. We have checked the conductivity of the material. You can see the small semicircle here. Small semicircle of means blue color is the optimized graphene BiO4 and molybdenum photoelectrode. It's showing the small semicircle means higher conductivity, means high charge transfer here. But if you can see the red color here, it's showing the graphene and BiO4. It is a little bit the conductivity is less as compared to the optimized graphene BiO4 molybdenum electrode. But if you can go for the pure bismuth vanadate, it's showing the low electrical conductivity. So when addition of the graphene and molybdenum, the conductivity can be increases. Then again we have tested this. We have again the PEC results are also tested by separation efficiency, and you can see the optimized graphene BiO4 molybdenum. It's showing the 3 times higher than the pure BiO4 electrodes. Also, you can see the consistent charge transfer efficiency results in figure in figure B. It is also shows that the higher oxygen and hydrogen production rate. Then we have also studied the IPC measurement of our synthesized photoelectrode, and it's showing that uh, the excellent photo response are observed in the range of 300 to 500 nanometer. Uh, in case of the optimized BIO4 and graphene molybdenum exhibit around 45%, and it is almost 2% 2% twofold higher than the pure BIO4. You can see figure E. It's showing the hydrogen production rate of the three component. First is the graphene and molybdenum and oxygen. Then graphene and bismuth vanadate BiO4 and BiO4. So this is the main thing in the paper, that figure E. Figure E is showing the you can see here we have produced a more hydrogen of graphene with BiO4 and molybdenum, and notably, our graphene BiO4 molybdenum electrode demonstrated remarkable hydrogen production activity, which is approximately 400 micromole centimeter inverse in 3-hour light exposure. Furthermore, actually, we have again checked the stability of the material by using chromoentrometry, and it's showing the 80% retention of photocurrent density even after 24 hours. This means that our material is very stable, uh, very efficient, and it is useful for high large scale hydrogen production. This is our current stage, what we are doing for photoelectron water splitting. This is we are producing the green hydrogen production from small scale. So now you can see the figure here, lab scale. Currently we are producing the hydrogen by small scale, but when our small scale work we already finished, and now we are moving forward to the large scale material. So we have already received a PEC test station, and still the PEC technology is still under developmental stage. So our aim is to produce the large scale hydrogen, which is very cheap, very green hydrogen production. There is no byproduct. So the test station is already we are already working on the test station with the large hydrogen production, like a semi pilot plant. And those systems are totally automatic with the connected with the gas chromatography. And lab scale work, we are converted this lab scale to the pilot scale, so that the TR level more than for six. This TVC technology is still development stage, but our technology is going to the under more than TR level 6 or 7. So still our now our technology is ready, but we are still optimizing couple of things, and I hope that our technology will transfer soon. Then I will move forward for my another work, that development of um, anode material for electrochemical water splitting. As I mentioned earlier, this is photoelectrochemical water splitting. So we have that developing efficient and low cost and environmental friendly electrocatalyst for hydrogen production is actually crucial for energy storage, energy generation system. So for the commercialization, the material should be a very cost effective. It is earth abundant, and if we can use the earth abundant electric catalyst, it's definitely it will be a cost effective. And this is a really urgent need nowadays. So to work this endeavor, actually we report the synthesis of polyaniline MW nanocomposite using a hydrothermal approach. And you can see the figure A, it's showing the XRD pattern of polyaniline and MnO4. MnO4 is also one of the like a promising material for electrochemical water splitting, because MO have a different oxidation state and it can be easily accessible for uh, uh, highly active electrocatalysis. So in that case, we have developed a electrocatalyst for electrochemical water splitting by using MnO4 and polyaniline. So we use the first we have synthesized MnO4 by using hydrothermal method, and then we use this MnO4 for making a composite with the conducting polyaniline. In the conducting polyaniline, we use the ratio of the conducting polymer is a 5%, 10%, 15%, and 20%. It's showing that the you can see in the XRD pattern, it is a pure MnO4. Pure NO4 in MnO4 peak. It is all the peaks are very well matched with the JCPDS peak, and we cannot observe any peak in the composite, maybe due to their poor diffraction of polyaniline. So we cannot observe any peak in the polyaniline and MnO4 composites. In the you can see the beauty of the SCM. You can see here figure A is the nanorod like belt like structure we observed in the MnO4, and figure B is the pure polymer. So figure C2F, it's showing the MnO4 and polyaniline. And here you can see after coating the polyaniline, we cannot see the bed like structure here, because there is a uniform coating of the polyaniline on the MnO4 here. So figure you can see the TM images of immunophora and immunophora polyaniline. In when we can move forward for the electrochemical properties, there actually 10% immunophore immunophore polyaniline it's showing the highest electrochemical properties, because of due to their high surface area, and the TM is showing the optimized sample of um, immunophora and polyaniline uh, composites. So figure A to H, you can see figure A and B is the TM images. You can see the like like bell-like structure, but and here you can see it is a pore structure of polyaniline. We have also studied check the SAD pattern, and you can see the elemental mapping. All the R elements are present here. Then we again tested this material for electrochemical water splitting. The resulting polyaniline immunophore nanocomposite, like 10% polyaniline immunophore electrode is a in. We have checked this material in alkaline environment like KYH we have used, and um, when we check the electrochemical property, it's showing that the in the you can see LSV curve, there is a low pore potential is observed. Means here there is a lower potential means more active catalyst. There is some difference between photoelectrochemical and water splitting, electrochemical water splitting. So if you can see here, there is a lower potential. Lower potential means there is a high production rate. So we have observed here the 10% optimized 10% polyaniline and ionophore composites, showing the high photoelectrochemical property as compared to the other polymer dope samples. So this is my collaborators. Now currently I'm working with this professors from different countries. Here my international collaboration, and this is my national collaboration. Currently we are working on that collaborator, and this is the opportunity in our group now in KENTECH also. So we are hiring the master PhD and PhD programs here. KENTECH, as I mentioned earlier, the KENTECH is one of the renowned research institute in Korea. This is totally funded by KEPCO and government of Korea. So the fellowship amount of master PhD and PhD is totally higher as compared to maybe any other universities, because this is just like basic cost. They are providing the extra accommodation if you can go get selected for any master or PhD program. So but there is some criteria that PhD student should have qualified the English language course, and there is another criteria: he should have a strong educational background, uh, and maybe he has published. This is optional. Maybe if you have some research background, it is welcome to join in KENTECH. So those who are interested, then please send the CV to uh, our my email ID. So thank you so much for your kind attention. Thank you.
Thank you, Dr. Mohseen Tamboli. It's very nice to hear and see your exhaustive research in the field of battery technology. And I'm very happy to see you here presenting last 1.5 hour. Very nice, very nice, and thank you very much. Is anybody is interested to ask the question? Please, the forum is open for the question answer session.
Participants can unmute their mic and directly ask the question.
Dr. Mohsin,
Yes.
I have very general question. As we are all using LIBs in our day-to-day life gadgets, and we always face the problem of discharging. So early discharging of all the gadgets here, isn't it? So, what care we should take to increase the life of batteries in mobiles and laptops?
Mm, Thank you, sir, for such a nice question. Uh, as we know that the lithium-ion battery technology is already commercialized, and the lithium-ion battery we are using in our day-to-day life, even though our smartphone we are using here. Generally, lithium-ion battery we can take care for actually taking care means there is a nowadays electrofabrication is one of the key issue for lithium-ion battery technology. Still, I have mentioned earlier the graphite is used, but as you asking me about the take care of the battery uh, charge day-to-day life. Generally, I would like to tell you one more thing is that the environmental can one of the impact for the discharging a battery. Environmental impact. Suppose now I am staying in Korea, so here the battery charging and discharging process it's quite difference in as compared to that our summer and winter season, because there is one reason is that in the winter season the chemical reactions very slow. In case of the summer, the chemical reaction is very fast. So if you can in India actually generally there is not that much up to the issue, but into day to day life if you can generally batteries that life cycle is around 300 to 400 times. So in case of battery, if you can charging and discharging time, if you can charge 80 to 90%, until for 300 to 400 times, that can be useful for your long time battery, like long you can use the long time battery.
Yes, 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 yes. So always when we buy a new product, the suppliers used to tell regarding not to charge fully 100%. Correct.
Yeah, yeah,
So
that is the reason.
yeah, yeah, yeah. So that was just from the expert. I was expecting the
Yeah,
the
thank you,
same
sir.
you have told. And one more question I'm having that as far as the hydrogen technology is concerned, how safe this hydrogen storage while using in vehicles particularly?
Yes, yeah, nice, and it's such a, like expected questions from you, sir. The thing is that currently we are using hydrogen as we like now. The now in Germany, they are hydrogen is using as a aeroplane and train nowadays in Germany. So hydrogen is going up to the mark there, but nowadays the storage of hydrogen is one of the key issue here. The thing is that generally nowadays hydrogen is using as a fuel cell. So uh, this is a safety issue and storage problem. So nowadays we are using hydrogen in the fuel cell. So fuel cell we can kept in the car. So there is not that much problem. It is safe. But if you can like directly use the hydrogen, it is really explosive and it will be immediately like um, like damage all these things. So we are using hydrogen, or generally day to day life, people are using the hydrogen in a fuel cell.
Yes, yes, yes. Thank you very much. So your exhaustive work with the many combinations for the anode material and its applications in the battery technology. So it's really great to see your work and research publications and all that. Thank you very much. Is there anybody still want
Sir,
to?
Nagaraj
Hello, sir.
T, sir, you can ask the question.
Sir, I have one question, sir.
Yes,
Sir, that actually that was a nice presentation, sir. You have done a lot of work and published in a lot of journals. Sir, sir, you just showed some slides regarding the battery applications. Sir, I have one basic question. Sir, what's the basic criteria to choose the material, sir, for a battery kind of applications? What is the basic criteria to choose the material? Uh,
yes. Hmm.
you
That,
showed some BVO4
yeah, yeah.
material, some
Yes,
MnCO1, so other materials. So, what is
yes.
the basic criteria to choose the materials?
Yes, basically in the battery, I'm just you are asking about the battery, because the battery there is some criteria is that the material should be semiconducting or conducting. Insulating
Mm,
material cannot be used because there is a no charge transfer there. So
okay,
the as we know, as mentioned, that the graphite is used commercially for commercial, like in your mobile also there is some battery, and the battery graphite is used as anode material. So
okay,
still graphite have some disadvantages such as a low specific capacity. So choosing the material such as that, nowadays people are going for lithium titanium oxide. This is one of the metal oxides. So we have to
okay,
choose the material with the semiconducting material with low cost. I'm talking about directly used for the commercial purposes. So but if you are talking about some just only research, we are like using lots of material for development of like anode material or cathode material. But if you are choosing for if you are going for the commercialization material, we have to think about the all aspect. For example, we have to check the cost of the material, we have to check the stability of the material, we have to check the efficiency of the material, and we have we have to check the easy available or earth abundant material. So generally nowadays if you can use the some semiconductor material, it will be useful for battery application like metal oxides.
okay, sir. Okay, okay, sir. Sir, and also some for purity confirmation. So we did XRD for our means for any samples. See, and suppose if the sample has some of the other peaks, okay, other than purity peaks, so we can continue our work, or we have to prepare once more the samples.
Actually,
Again, we
when
have to prepare the sample.
yeah, actually you are asking about the impurity peak, right?
Oh yes, sir.
Yeah, if there
Because
is
in
impurity peak there,
one
we
of the
will take,
sample MCO,
yeah, yeah.
and in that sample I observed some one minor peak other than the indexed peak.
Yeah, yeah,
Suppose
but there is
if such
no,
kind
there is
of
no impurity peak. There is no impurity peak. There is a
uh,
peak. There is a that's a good question. Actually, you are like observing very carefully. So I explained that there is a one peak with the higher nickel doping, means like 10, 20, 30, or 40. If I go the higher loading of my nickel, like nickel cobalt oxide into the BiO4, because of the higher concentration, we observed a small peak of 100%. This is the
okay,
reason. But there is
okay,
no impurity peak.
okay, sir. Okay, but that is not indexed in that sample, right, sir?
No, we
So
in my
if it is
experimental
not at all
indexed.
the impurity MCO, some MCO, MNCO one that series
Okay,
sample.
okay. I will look the presentation. Okay, I will open that.
But exactly, I don't know the slide
There
number,
are too
but
many slides.
that MNCO1, MCO, that samples.
Okay, okay. Maybe there is no impurity peak actually. Maybe due to the higher loading of the peak. So maybe I will check.
Okay.
Or you can also, my slide is just 1 minute.
Oh. Sir, okay, but if possible, you can show, or otherwise it's okay, sir.
Yeah, it's okay. It's okay. I will show.
See, sir, around 51 degree Celsius. So this is not the sample. Around 51 degree Celsius, I observed some minor peaks.
Here you
So
are
is
seeing,
that,
right?
yes, sir, around 51, 52. Not 50,
You
around
can see
53.
here. You can see here. There is a MCO peak. As I mentioned, there is 100% peak. You are see the label. We have already
Sir,
done.
this is not the sample, sir. MCO,
Next.
MNCO1. So that
Oh,
sample.
yeah, yeah, yeah. This one, right?
This is not the one more series set of samples.
Okay.
This is the one, sir. See,
Yeah, yeah.
in the first sample, around MCO, around 42 degree, one minor peak is there.
Yeah, there
So,
is a thing is that there is a both NiCO24 and MnCO24, both have a spinel structure. So this
okay,
XRD, it's showing that the according to the manganese cobalt oxide spinel structure.
okay, sir,
I
okay.
understand
Okay,
because
sir, okay,
here
sir.
there is no any other phase. They like NiCO24 and MnCO24. It's showing that both are the spinel structure.
Okay, sir, okay.
Okay. Thank you so much.
Okay, sir,
You are
okay.
like observing very carefully.
Sir, thank you, sir.
So thank you, participants. Thank you, Dr. Mohsin. Uh, it's time to wind up the session. So I thank on the behalf of Sri Siddheshwar Devasthan and our college, our management, our trustee for accepting the invitation to deliver here your exhaustive work in spite of your busy schedule, right from the uh, South Korea, as you are very busy in your research work, and that's why I'm very much thankful to you. And I hope all the participants have enjoyed your session. So thank you very much, sir. and see you again. Thank you.
Thank you so much. Thank you for all. Thank you.
Okay, participants, we will end the first session, today's first session, that the session number 3 overall. And within 2 minutes, we will start the today's second session, which is of Dr. Swanand Kulkarni. He's already joined here, and um, is there, sir? Are you there?
Yes, yes, I am present, sir.
Yes, yes. So thank you very much, sir, for joining timely and without wasting much time. I take privilege to introduce you. So on the behalf of all the participants, our management and our college, I am very much thankful for accepting our invitation, and I will introduce you here that. Sanand Gajanan Kulkarni, an accomplished academician and researcher, currently serving as an associate professor of mechanical engineering at SKN Sinhagad College of Engineering, Koti, Pandharpur. Dr. Kulkarni holds a PhD in mechanical engineering from Sardar Vallabhbhai National Institute of Technology, Surat, awarded in March 2017. With a rich career spanning 23 years, Dr. Kulkarni brings a balanced blend of 4 years of industrial experience and 19 years of academic expertise. He has taught 11 different subjects and is an active member of professional bodies such as Indian Society for Technical Education, the Institute of Engineers of India, and the Indian Association for Computational Mechanics. Dr. Kulkarni's research contributions are exemplary, with 17 papers presented at international conferences, 38 papers published in the international journals, 4 book chapters, and 3 edited books. He also holds 2 granted patents, showcasing his innovative approach to engineering challenges. In addition to his academic pursuits, Dr. Kulkarni has completed 6 funded projects, including TBT, seed money, and UBA initiatives. He has worked as remote center coordinator for IIT Bombay and IIT Kharagpur, organizing 21 seminars, workshops, and conferences. Served as a convener for the international conference ICSICM 2020 and as a coordinator for an issue of prestigious journal Material Science and Engineering by LOP Publishing. Contributed as a Board of Studies member for Punyashlok Ahilyadevi Holkar, Solapur University. Dr. Dedication to Kulkarni's dedication to research, innovation, and education makes him a true asset to the academic community. We are honored to have him share his expertise with us today. So please join me in welcoming Dr. Swanand Gajanan Kulkarni. His talk will be on fabrication and characterization of AMMC. Over to Kulkarni, sir.
So, thank you very much, sir. Am I audible?
Yes, sir, you are audible.
Slides are visible, sir.
Uh, the first slide is visible. Make it full screen, sir.
Yes.
Right, slideshow vision. Yeah,
Is it changing?
yeah, it's there. It's visible now.
Okay. Thank you.
Yes, you can
Thank you very
start.
much, sir. Thank you for inviting me for this wonderful Atali FDP, because taking the efforts to write such a wonderful proposal, to granting it, and taking efforts for such a nice workshops. Always helpful for the community, always helpful for the society, always helpful for the particular engineering premises which are working around us. This composite material is an emerging area, and we are taking some overview on this composites today. Uh, So good efforts by this Siddheshwara Engineering College, and I am thankful to Madki sir, Patil sir, Dr. Chavan sir, and all members of these institutes who have taken efforts for this ATAL FDP. As far as concerned with this today's session, this is the fabrication and characterization of aluminum metal matrix composite. So if we take the scenario on this composite, then we comes to know that this composite word that is useful in many areas. So composite in terms of mechanical engineering, composite in terms of civil engineering, composite in terms of electronics and telecommunication, because wherever material part is there, in all cases we required to go for the composition of new material, because every technology is demanding always the new materials, and new materials comes with this kind of research which we conduct from our labs. And whenever such a new materials are innovated, then that replaces to the previous materials. So as far as concerned with 1980 1990, in this era, the car was having the weight near about 900 kg, and recently we are observing that this car weight is near about 550 to 600 kgs. This 300 kg of weight saving has given rise to the good mileage, good energy saving, and this is one kind of sustainable development. So indirectly such materials or novel materials or composite materials always supports for the sustainable development also. So many areas are there. We are taking to take one small review on this, which different areas on which this particular composite materials has taken the advantages. As far as concerned with the history, we know that always in our historical region we learn the two civilizations, that is Mohenjo-daro and Harappa. These are the civilization in Indus valleys, where there were the constructions were found, and that constructions were the evidences of the composites. If you see the Exodus, so here one statement is given that you are no longer to supply the people with straw for making the bricks, let them go and gather their own straw. So this gives the example where the different kind of materials are composed together to give rise to new material. So these kind of evidences always use the evidences that composites were used in historical days also. As far as concerned with historical examples of the composites, these are abundant in literature. Use of reinforcing mud walls in house with bamboo shots glued laminated woods. These are some of the examples, or as far as concerned with forging swords. In alloys and composites, always in Indian culture, there was amazing research was conducted. We know the Ashok Stamba is one of the example, and it is giving the composition of good alloy, which is present in all environmental widely, and in that also again for 2000 years. So there is no certain amount of any corrosion, there's no certain amount of any erosion for this good composition of the alloy. So which gives the strong evidences of the history where the materials or alloys and composites were used in the Indian history. But as far as concerned with modern era in 1970, again there was large changes in this composites world, and many composites were come ahead, and particularly today we are going to observe the aluminum matrix composites that refers to the class of uh, so as far as concerned with this aluminum matrix composites, so it refers to the class of lightweight high performance aluminum say, material system. Particularly when we think about the aluminum matrix composites, then it founds that aluminum is the matrix material. For composite materials, two kind of materials always take the contribution, out of which first contribution is related with the matrix, and matrix is one of the very important component in aluminum matrix composite, because what happens, if we change the matrix, then definitely that matrix gives the rise to the different properties. Aluminum has its own identical properties, and particularly whenever we think about automobile sector, whenever we think about aerospace sector, we take the example of sporting industries, marine industries, then this candidate is considered to be a very good candidate, because aluminum is having very less density. Aluminum and its alloys are unique, and they have flexibility in different directions, like corrosion resistance aluminum is there, wear resistance aluminum alloys are there. Then aluminum with 7075 kind of composition is having good strength. So whenever we want the different compositions of the aluminum alloys, we take advantage with reference to its property content. So here particularly we are focusing on aluminum matrix composite, because particularly aluminum is present in abundant quantity in Earth's crust, and particularly it is having one very lightweight composite, because in case of, if we compare with the iron, it is having one third of its density. So more always focus is given on the aluminum. As far as concerned with the reinforcement in case of this composite materials are in many types. If we take example of particulate, small particles are introduced in the matrix material. If we take the example of short fibers, very small fibers are there, and that fibers are added. If we take example of long fibers, then that long fibers are added. Continuous type of composite materials are also there in composite, continuous type of material. Reinforcement are in continuous manner, monofilament type of manner. So these different kind of composites with reference to the properties of matrix material and with reference to the reinforcement materials are always there. Again, aluminum matrix composites are having advantage to tailor to the demands of different industrial applications by suitable combination of this matrix and reinforcement. At the same time, processing route also plays an important role, because unless and until proper processing routes is not followed, the expected properties cannot be achieved. Now, different grades of aluminum matrix composites are manufactured by different routes, and same kind of technology we can use for the composite manufacturing also. So, 5 decades of intensive research have provided a wealth of new scientific knowledge on this intrinsic and extrinsic effect of ceramic reinforcement. So, these aluminum matrix composites always helpful for the different type of compositions, and that compositions are always useful for changing its physical properties, mechanical properties, thermomechanical properties. Here, if we take the example of this one, the advantages, particularly why to choose this aluminum matrix composites, or why to give the advantage of this particular composites, we'll come to know that the advantage can be quantified for better appreciation. So here, if we take the example of this particular composites, particular if we take this aluminum matrix composites, any kind of series, 202 series or 30 series, 4 series, 5 series, 6, 7 series, all kind of series have their own identical property, where they may be used for particular strength application, may be used for corrosion resistance applications, and many more type of applications are there. So as far as concerned with this particular case, where we are now observing the case of aluminum matrix composite here we can see that these composite materials are having advantage of elastic modulus in pure aluminum, and that can be enhanced from 70 gigapascal to 240 gigapascal. So see what advantage of composite we can take with reference to the addition of this reinforcement percentage. So when 60 percentage of volume is added in aluminum fiber inside the aluminum, we can enhance the property or elastic modulus of pure aluminum from 70 gigapascal to 240 gigapascal. We take another example. If 60 volume% of alumina fiber in pure aluminum leads to decrease the coefficient of expansion. So the first application is useful in case of strength or structural application, we can say, because here the elastic modulus has been increased. And in second application, if we take the example, then we can consider that this can be used for the thermal application. So thermal applications mean electrical industries or in electronics industries that can be used. So that's why these kind of materials are very versatile type of materials which can be used in various type of industries based on the combination of matrix and reinforcement material. If we take the example of a particular alumina 9% silicon 20% SiCP composites, then it is useful in case of wear resistant applications. So in general, there is a trend that we are using the gray cast iron, and there are that gray cast irons are used for wear resistant applications. But if we go for the composition, if we go for the manufacture of composite material, in which if we use this reinforcement which are having good wear resistant applications like silicon carbide, then this gives the wonderful properties of wear applications. So all these kind of examples illustrate that it is possible to alter several technological properties of aluminum alloy, and we can have the composition which incorporates appropriate reinforcement in suitable volume fraction, and that gives rise to change in various kind of properties which we expect. So based on the application area, we will choose our matrix, our reinforcement, and our manufacturing routes. Here, as already discussed, or we are going to discuss in further that type of reinforcement and type of matrix. The properties of aluminum matrix can be tailored to demand of different industrial applications, and presently several grades of aluminum matrix are manufactured by different routes. So, see, the large parts of aeroplane turbines, windmills, that are different to analyze, so that can be manufactured. The effective failure analysis of all parts can be done by applying same load conditions here. Some of the composites which are used for aerospace industries, for automotive industries, for marine industries. As far as concern with this composite material, always there are some advantages and some limitations for these composite materials. Means if we take this, if we observe this particular slide, we'll come to know that particularly if we see this hatched section, so all these hatched sections are the ceramics. And if we see this particular portion of metals, then composite is shown in between all of this. If on one side we are measuring the strength of the material, on another side we are using the affordability of the material, on another side we are using we are measuring the corrosion resistance of the material. Then secondary process like joinability, formability, then toughness of the material. Then we will come to know that on each front of all these kind of property, because these are needed, and these needs are based on the type of particular application. Suppose we are interested in strength, always ceramics are having good strength, but the ceramics are having limitations of the formability. At the same time, for the metals, we have good secondary operations like joining or welding techniques in case of metals, that can be done properly. But at the same time, the strength as compared to ceramics for metals are less. If we take the example of these composites, then in particularly aluminum matrix composites, what happens that whenever we add the ceramics inside the metal, then it gives the properties which are in between that. That is always works with the rule of mixture. So see, rule of mixture means what? Whenever we add the ceramics, the strength of these metals will increase. Means particularly this metal are having, if this is the strength, then due to addition of this ceramic, the strength of this material will increase, and this increased strength will give the composite material with good strength as compared to metal. So that becomes the advantage of the composite material. At the same time, due to addition of these ceramic materials, some limitations for this composite may happen, but particularly based on the application, we have our particular composition. So always this is working with the rule of mixture case. So here we can take the example of these metals and alloys, maybe steels, aluminum alloys, aluminum, copper, brass, titanium. All these metals are used for composite manufacturing. In that, if we add the ceramics, because ceramics means what? The borides, nitrides, carbides, oxides, all these are the considered to be a ceramics. And all these ceramics we can add inside any metal, which will give the property of the composite material. So here, if we see the intersection of these metals and alloys and the ceramics, then this intersectional part will show the ceramic reinforced metal matrix composite. Particularly if we add the carbides, suppose silicon carbide we are adding, then this carbide is the ceramic, and that ceramic we can add inside the metal, and this particular composition will give the rise of composite, and that composite which can be used for any particular application. So based on the type of ceramic and based on the metal, this composition is possible. So this intersectional area will give you the composition of particularly the this metal which is present inside this domain and the ceramic present inside this domain. So in that ceramics, maybe we take the oxides, borides, nitrides, and like this. So one more part of this plastic is also present here. So composition of plastic and metal is possible. Composition of plastic and ceramic is also possible. Composition of ceramic and metal is also possible. So all these intersection gives the composites which are possible with this different kind of compositions, and this based on the different applications we are using. So here we can take this based on the matrix. Maybe metal matrix composites are there, ceramic matrix composites are there, polymer matrix composites are there. If we are using the matrix of various polymers like polytetrafluoroethylene, polyoxymethylene, or any kind of polymer, if we are using as a matrix material, then that is polymer matrix composite. If we are using the different metals, then this is metal matrix composite, and if we are using the ceramics, then these are the ceramic matrix composites. So again, based on the size, suppose reinforcement size in particle type, then that is particular type of composite. If it is short fiber, then fiber type of composite. Long fiber, so short fiber, long fiber, monofilament, and laminated is one of the beautiful composite. In that, one lamin of matrix material, another lamin of reinforcement material. Like this, laminated composite materials are also there. So if we see this classification, we come to know that this composite is a very vast area, and based on the applications, we can have this kind of flexibility. So here we take the example of this particular composites, where these particles which are embedded inside this matrix material, maybe these are the discontinuously reinforced metal matrix composites. So here we can see these are the discontinuously reinforced. So maybe that materials isotropics, or these materials are anisotropic or transversely isotropic. Like this, properties of the materials depends based on type of reinforcement we add inside this matrix material. So maybe flakes are present, short fibers are also present, or maybe fibers composites which are such as long fibers which are from face to face, from one face to another face. Like this, these fiber composites are also there, and monofilaments are also there. So based on this type of composite material, this we can have the flexibility to use the particular composites. So here we can take the example of this gas turbine engine components made of metal matrix composite. particularly Honda and Toyota. So these two automotive industries initially started to use the metal matrix composite, and particularly for brake drum application and particularly for piston cylinder applications. Previously, these metal matrix composites were used. Here we can see the example of gas turbine engine also, where this metal matrix composites are used. Based on the particular property, because composite materials have advantage to change the physical properties, composite materials have advantage to change the chemical properties, composite material has having advantage to change the mechanical properties as well as wear resistant properties. So all kind of properties which we expect that we can change, we can add, we can reduce. So maybe thermal properties, maybe electrical properties, mechanical properties, tribological properties, physical properties and chemical properties. All kind of properties we can change based on the proper composition and manufacturing processes. So here you can see, so this what is the role of matrix material. So as far as concerned with the matrix material, the base material which forms the percolating network, so functions of the matrix, because if two phases are there, then what is the role of each phase? So that we need to understand, because matrix material is one kind of binding material, and its function is to hold the fibers together. So whatever the reinforcement we are adding inside the matrix material, all these reinforcement particles may be of any shape, any size, to hold that fiber material together is the function of the matrix material. Then that matrix material protects the fiber from environment. Means this matrix material becomes one kind of cover for this reinforcement of this fiber, and this protect this particular fiber from the environment. At the same time, it distributes the load evenly between the fiber. Whenever load is applied on this composite materials, then the matrix is not used to take the load, but it will transfer that load toward the fiber material, and fiber materials will bear that load. The role of matrix material is only to transfer that load toward the fiber material, and that fiber material will have the role to accept that load, and likewise to improve the impact and transverse resistance. That is also this matrix phase. At the same time, for reinforcement phase, this is embedded in the matrix phase. So function of reinforcement is to improve the chemical compatibility, to improve the thermal stability, to enhance the mechanical strength, and to improve the electrical conductivity. So maybe the which kind of property we are interested in, based on that the reinforcement phase is selected, and what kind of properties we are interested in, based on that matrix phase, that are also. So the combination of this matrix and reinforcement phase is very important, and it is totally based on what kind of property we are interested in. So for chemical compatibility, for thermal stability, for mechanical strength, and for electrical conductivity, this reinforcing phase is useful. So
Hello, sir. There is a network issue, I think, from the Kulkarni sir. Let me check. Please stay on. Sir will join quickly.
Am I audible, sir?
Yes, sir. Yes, yes, sir.
Okay, okay.
Let me make you host so that you can
Yes, 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 sir.
share the screen. Yeah, yeah. You are already. You are already. You can share the screen now.
Yes, yes. Okay. Thank you, sir. So, will you, sir, tell me for what, from which slide I was out the from this session? Patil, sir.
Yes, you are right. Go on, sir. Go on.
So,
I think more slides are there. Still more further.
yes, yes.
This,
So, is this part was covered, that matrix and
yes,
reinforcement?
covered. Yes, sir. Covered. Covered.
So, as far as concerned with this future of the metal matrix composites, so in 2031, it is expected that present market will be more than 7.2% as compared to 2024-2031, and the areas not only for the automotive sector and aerospace sector, but for defense application and particularly for renewable energy, for electrical vehicle, this will be very useful type of metal matrix composites. The factors that will drive the growth, because lightweight, then manufacturing technologies, then sustainable materials, new material combinations, self-repairing type of materials. So these are some of the requirement of the technology, and that the particular metal matrix composites will fulfill the need of the technology, because not only lightweight material, but as far as concerned with this healing technology or self-repairing type of materials, so that is possible with reference to this metal matrix composites. So particularly for these different sectors like aerospace, automotive, defense, renewable energy, and electrical vehicles, these metal matrix composites will be particularly useful. And as far as concerned with these different properties, so here we can see that if reinforcement are here and matrix is here, then composites holds good in between these two. The composite materials has the properties in between the matrix and fiber material, because it works on the rule of mixture. Whatever the percentage of reinforcement get increases inside the matrix material, then appropriate the which property we expect, that property of the matrix material and the reinforcement material, in between that, based on the fiber percentage and based on the matrix percentage, the composites bears that particular properties. So maybe as already stated, that if it is thermal or electrical or mechanical or tribological, physical or chemical, based on the percentage of that reinforcement in the matrix material, that are always having in between that two. So particularly for aluminum matrix composites, it is lightweight, high performance, and properties of aluminum matrix shows the considerable change of reinforcement. So particular, if we see the different advantage of this aluminum matrix composites, coming to the processing of aluminum matrix composites, so here solid state processes and liquid state processes, these are the two major processes through which we can manufacture the composite materials. As far as concerned with the solid state processes, the matrix material and reinforcement material both are taken in terms of particles. Small particle formation of composite is done with the help of this powder metallurgy technique. So powder blending and consolidation, or powder metallurgical process, or diffusion bonding process, these are used as a solid state processes. Inside that, in simple way, we can manufacture the composite material inside this matrix in particulate form and in powder form. Reinforcement in powder form, both are blended together. Proper mixing is ensured with proper blending techniques, and later on the compaction and sintering processes are carried, and this composite material with particular maybe any shape, for that these solid state processes of powder metallurgy are useful. Presently we can use the 3D techniques also, because as far as concerned with this metal matrix composite, now the technology not only for polymer but for metal matrix composites also, for metals also, we can use this 3D techniques, 3D printer techniques, and with this also the solid state processes can be done. As far as concerned with this liquid state processes, the stir casting is one of the best methods. Infiltration process, pre-deposition method, in situ processing, squeeze casting is also used. Two-step stir casting is also used. So all these processes from stir casting to infiltration, spray deposition, in situ processes are used as a liquid state processes, and that are conventional type of processes which we can use for manufacturing of this composite material. So particularly if we see where this metal matrix composites are used, so for boron aluminum material for this aerospace sector, here we can use the example for in case of this boron epoxy reinforced titanium truss members that are used here. So likewise, you can see the various composite materials which can be used for aerospace sector here. Now, here we will take small review on the fabrication technique which is used in case of metal matrix composites, and for that purpose we'll take the example of suppose A356 which was used in the one of the experimental investigation, and for that purpose A356 material, particularly this material is having 7% silicon present inside this material, and due to which this this is used for aircraft and automotive due to its high strength weight ratio. If we take the example of this tensile strength of this particular A356, or if we take the applications of this A356, then these are used based on strengths for high strength airframe and space frame structural parts, machine parts, truck chassis parts, high velocity blower or impeller, aircraft pump parts, automotive transmission cases, aircraft fitting and control parts, water cooled cylindrical blocks. So A356, due to its unique properties, this alloy with 7% silicon in aluminum having good castability, and that's why this gives more advantage in stir casting process. So, as far as concerned with this designations of this whatever the constituents present inside this A356, this designation A356 is used. Particularly copper 0.25%, magnesium to 2.25 to 0.45%, manganese 0.35, silicon 6.5 to 7.5, ferrous 0.6, zinc 0.35, titanium 0.25, and others 0.05, and balance is aluminum. Like this is the composition of A356. Mechanical properties of the A356 material, so 2690 kg per meter cube is the density of this particular A356. So as compared to ferrous, so we can consider that very low dense material it is. Its Young's modulus pure in pure form is 70 gigapascal. Then its Poisson's ratio is 0.3, which is like our general metals. Its Brinell hardness is 70 for 500 kg. In particular, this case, alumina or aluminum oxide is used for increasing its strength, hardness, and toughness. So, aluminum oxide is commonly referred as alumina, and it possesses the strong ionic interatomic bonding which gives rise to desirable material characterization. So, alumina in case of A356 is very useful, it is very suitable, and many applications in which this alumina has been used along with A356 in order to improve the properties of the A356 to form as a composite material. So it is alumina is having high hardness, excellent dielectrical properties, then good thermal properties, and its availability is also good. Particularly when we go for the manufacturing of the composite materials, there are the different techniques inside which we have seen that stir casting is one of the way, then squeeze casting is another way, then infiltration process is there, two-step stir casting process is also there. So these are some liquid stage processes. For this alumina, if we take the properties, if we see the properties, then 3960 is the density. Then Young's modulus is 370, ultimate tensile strength is 300, Poisson's ratio is 0.23. Particularly here density is somewhat more than the 356, but if we see the Young's modulus, then it is 370. In case of 356, it is 70. So from 70 to 370, if this particular alumina is added inside this A356, definitely that Young's modulus are going to improve. Ultimate tensile strength, which in case of this alumina is 300 gigapascal. So if alumina is added in a 356, then definitely this will be useful for the structural application, because Young's modulus is going to improve and ultimate tensile strength also, as per the rule of mixtures of the properties. So this particular experimental setup which is used in present investigation, so for that purpose we have the composite manufacturing or composite fabrications. For that purpose, these are some of the process parameters for which it is attention is needed to be given, particularly for stir casting process. Whenever we use this particular technique of the stir casting, first of all we will go for the setup of the stir casting process, and then we'll come to back on the different parameters. So here you can see this is the stir casting process in which this metal is present inside this crucible. Inside the furnace, this is the crucible is shown. In that crucible, this is metal in liquid form. Particularly, we have seen that in case of metal matrix composite manufacturing, two kind of processes, inside which one is the solid state process and another is the liquid state process. So solid state process is the type of process in which the composite is manufactured with matrix and reinforced are in solid form. But in liquid state process, this matrix material is in liquid form and reinforcement is present in the solid form. So if you see this crucible present here, in that crucible, this metal which is in melted form, because after this 700 or 650 degrees centigrade is over, this all kind of aluminum and its alloy starts to melt. Near about 700, this total melting process is carried. And after the melting, then if required, the degree of superheat is also given, because superheat temperature always helps for the material to become stable, to remain stable. So many times this temperature is kept as 800 degrees centigrade. For 800 degrees centigrade, this once melt totally melt is over and 100 degrees superheat is over, then the process is carried. In that processes, before adding the reinforcement, it is seen that any slag is present, that slag is removed. If any oxidant oxides, if it is present on the layer, surface layer, then that are removed. So grain refiner tablets may be used in order to having the good grain size, because if grain size or secondary dendrite arm spacings are better, then definitely materials are having good properties. Smaller the grain size, better is the mechanical properties of the material. So grain refiners are also added here. This is the reinforcement adding arrangement which is shown here. Through this hopper, these reinforcements are added here. So once that reinforcement is started to add here, at the same time this particularly stirrer which is present inside this crucible, that starts to rotate, and then this composition of metal and reinforcement mixing starts here. Once that is over, then this mixture is poured inside the mold. So stirrer is present here, liquid metal is present, this is crucible, these are the heating coils and furnace covers, and this is the motor. If we take example here, you can see the one of the composite manufactured in the lab. So you can see here, this one is the composite. I think you can can see here, this is the crucible, and particularly now I think some problem is there. It is not playing, but this kind of small pieces of this matrix materials are added inside the crucible, and after adding this crucible material here inside this material, then stirring process is carried, and after stirring process, this proper mixing is ensured, and once ensured, either from bottom pouring facility or with the help of this crucible pouring facility, this is achieved and this material is manufactured. The which parameters are important while the composite fabrications are that what is the reinforcement size, because based on the reinforcement size, properties of the composite material changes. Then what kind of stirrer is used, because stirrer is having different designs, so based on the stirrer design, what stirring speed you are using, that stirring speed also affects on the composite manufacturing process. What is the stirring temperature, that is also plays important role, because if proper superheating temperature is given, then properties are better. What stirring time we are using, because if proper stirring time is not used, then proper mixing will not happen, and expected properties will not receive, because at the same time this reinforcement material must be mixtured properly in the matrix material, and then only the proper amalgamation will happen, and we can have we can ensure that distribution of this reinforcement particles inside the matrix material has been happened properly. If that distribution is not proper, then whatever the composite gets manufactured, for that composite manufacturing, suppose the reinforcement materials get aggregated at one end and matrix gets aggregated on another end, then whatever the expected properties that doesn't comes. So for that purpose, the reinforcements proper mixing inside the matrix material is very very important. Unless and until that not happens, the desired properties we cannot achieve. So for that purpose, this stirring time is very very important. Then preheat temperature of the mold is also important, because this material we are going to pour inside the mold, and if this mold is at room temperature, and whatever the material we are pouring inside this one, if that material is at 800 degrees centigrade, then suddenly it cools, and due to the sudden cooling of this, particularly what happens that the porosities arises, or improper mixing arises, or gases which are entrapped will form the porous material. So for that purpose, the preheat temperature of the mold is also ensured. Unless and until we not give the preheating to this mold, the whenever we pour the material, when we pour this metal in, uh, this proper mixing is not possible. So what is the reinforcement feed rate? That is also one of the important component, because if sudden mixture of this reinforcement is added inside the this matrix material, then amal again this coagulation or this reinforcement which gets collectively formed inside this material, and due to which these properties which we expect, that properties will not desire available. So for that purpose, reinforcement feed rate is very very important part. Unless and until this is not ensured the proper reinforcement rate, then stirring time, stirring speed, and at the same time reinforcement feed rate. So preheat temperature of the reinforcement is also important, because whatever the reinforcement we are adding, if that are at room temperature, and if matrix material is at 800 degrees centigrade, then proper wettability doesn't happens. So for particularly to manufacture a suitable composite material, whatever the reinforcement we are adding, it should have good wettability in between these two phases. This wettability is achieved with this preheat temperature of the reinforcement. So for that purpose, this is one of the important parameter, that like mold, This reinforced material should have also proper free heating temperature, and by ensuring that preheating temperature only, the properties of this material, composite materials will be suitable properties. One of the important again parameter is the pouring rate. So the rate through which we are pouring the material inside the mold, so that is also one of the important tasks. So while composite fabrication, all these parameters are observed keenly so that desired properties of the composite materials which we expect that should come, because only matrix material and reinforcement material, the selection of matrix and reinforcement material, that is not sufficient, but we need to give attention on all these parameters which are various important parameters of which are very important aspects of manufacturing process of the composite material. So that's why all these parameters, unless and until we not study keenly and we not select properly, the whatever the desired properties of the composite material we can't ensure. So particularly, if we see here, this is the procedure, the process followed, placing this particularly ingot forms of these materials, because whenever material we take from the market, the material is in ingot form. So that ingot forms materials are first cleanly properly, then cut into the small pieces, whatever the expected pieces, then that are placed inside the crucible. Then heater temperature is gradually increased up to 800 degrees centigrade, so that simultaneously melting of these ingots will happen. Then material properties of the reinforcement and matrix material. So reinforcement preheating is simultaneously observed, because what percentage we expect. In general, whenever we carry the experimental investigations, we have certain percentage which we have decided earlier, that percentage we have to add. So that's why weighing of that reinforcement material is properly carried, then weighing of matrix material is properly carried, then expected weight of this matrix material is ensured, expected weight of reinforcement is ensured, and once that materials are kept inside the crucible, then preheating of reinforcement is also simultaneously observed, that preheated reinforcements are added inside this material at semi-solid stage. Suppose for 650 degrees centigrade, sometimes for magnesium is also added. The purpose of addition of the magnesium is to improve the wettability, because if wettability is proper, then bonding between matrix and reinforcement is better. Unless and until that wettability is not ensured, this bonding is not achieved. So for that purpose, magnesium by 1% is added, and at the same time degasification powder or grain reinforcement powder, that is also added. Degasification powders are added in order to remove the gases entrapped, or if any oxide layer is generated on the surfaces, then in that cases the degasification tablets that are useful. Grain refinement tablets are used because that is one kind of chemical reaction with the grains, and that grain formation happens. So smaller the grain size, better the properties. So for that purpose, in this liquid process, or in particularly the stir casting process, these grain refinements are generally preferred in order to have the better mechanical properties. And then the scum is removed. After removing the scum, then stirring at this particular RPM, specific RPM, which we have decided from previous research or from our experience. So that stirring speed in terms of RPM is decided, and that stirring for particular time is carried. Maybe that is from 5 to 10 minutes, many times 10 minutes is carried, or in case if it is sufficient for 5 minutes is also carried. That RPMs are from 300 to 450. In some cases, 500 RPM is also used. So based on the matrix and reinforcement material which is used, that what kind of speed is should be used preferred, and for what time that reinforcement should be used, or for that stirring process should be carried, that is decided. So the addition of reinforcement is simultaneously done with this hopper during the stirring process, and addition of reinforcement for that reinforcement rate through which we are adding this particular reinforcement, that is ensured, because unless and until we not ensure the proper addition of reinforcement rate, then the proper amalgamation of or proper mixing of these two phases is not ensured properly. So for that purpose, this reinforcement rate is very important. That should be also decided based on which type of reinforcement and matrix material is there. Then once that process is over, then this molten slurry is poured inside the mold. So at the same time, it is ensured that mold should also be preheated, and that preheated mold is kept near to this particular crucible, and this crucible is used and that is poured inside this molten slurry is poured inside the mold. So we expect the different cast properties. If we are we expect that plate shape, then plate type of mold, and if we expect the round shape, then this bar type of molds are used. And like this total fabrication process is ensured. So once that fabrication process is carried, then particularly maybe plate type or maybe in case of round shape type of materials that is seen, maybe a round type of materials or this rod type or plate type of material once ensured, then the secondary operations are required on that. Means whenever we go for the characterization of such materials, then in that case, what kind of tests we are interested in, based on that, these secondary processes are carried on this particular plate shape or this bar shape, and various tests are carried. Maybe while carrying that different characterization or various tests, different standards are used. Maybe Bureau of Indian standard used, maybe German standard used, maybe British standard used, or American Society of Testing of Material ASTM standard is used. So for this composite material, whatever the referred type of ASTM test standards or British standards or Indian standards, that test standards we use for prepare the this particular specimen. And this specimen, for example, if we see here, this is one of the B557 type of ASTM test standard. Inside this tensile test is carried. In general, we observe the tests in case of this test standards, maybe round bars are used, but here these are in small plate size. So here you can see for tensile test, this ASTM B55 test standard was used in this present investigation. And this tensile test is used to assess the mechanical behavior of the composite and matrix alloy. So according to this test which is decided here, these are some of the guidelines provided. So based on the guidelines which are provided here, we can see what is the total gauge length, what is the width, what is the thickness, what is the radius of fillet which is used here, and what is overall length, then what is the length of reduced section, then what is the length of grip and width of the grip. So all these parameters are very, very important because these are always proportionate with each other. And suppose in this particular case, this gauge length used was 25 mm. Then this particularly length at the grip side, this B part is the grip side, and this is 30 mm on both sides. Then here you can see the length of reduced section. This A part is 32 mm, so 25 mm is gauge length, but this A, which is the length of reduced section, that is A 32 mm, and total length, which is overall length, which is considered to be 100 mm, width is 6 mm. So here we can see the thickness is also 6 mm. So these are the standards. Here width of the grip section is also 10 mm. So here you can see that these guidelines are used based on the test standards, and that test standards are as per the guidelines provided by the maybe ASTM test standard, which is in present case, but we can use Indian standards also, we can use the British standard, German standards also. So at the same time, which kind of specimen which are interested in? Suppose we are interested in the bending strength, then the suitable characterizations of the bending tests which are given by the ASTM test standards that we will use. Maybe different methods or the different experimental conditions based on the design of experiment. Already we decide some design of experiment parameters. In that case, we use which kind of parameters, which kind of levels. And once that is decided, then with that design of experiment methodology, which we expect our results based on that, we carry the experimentation. Once that experimentation are carried, then based on that experimentation, we expect the results. So different kind of testings that are carried as already stated by the different test standards. One more technique we can use in order to have the proper validation. So for that purpose, nowadays, we can use the theoretical method. So in case of composite materials, two important approaches are there, out of which one approach is micro mechanical approach and another approach is macro mechanical approach. In case of micromechanical approach, the properties of matrix material and properties of the reinforcement material are taken into consideration, and based on that, the properties of the composite materials are decided. The properties of the composite material are calculated based on the theoretical micromechanical approaches. So that are applied for this particular specimen which we are conducting the experimentation, and then these tests are carried, or this particularly analysis is carried. So this is the theoretical analysis. So that theoretical analysis is used with particular geometry which we use from the test standard, and from that we can calculate the tensile strength of this particular material, and we have the experimental validation with particular testing in the labs. At the same time, we can have this bending test, buckling test, tensile strength, compressive tests, wear and hardness also. So for that purpose, this is one of the technique which we use, that is the micro mechanical approach, and based on that composite properties. Another is macro mechanical approach, and for that macro mechanical approach also, we can carry out the finite element analysis, and based on that also we can predict the properties of the composite material, and that is the modeling method in order to have the theoretical analysis of that particular composition. So many times different rule of mixture, so the different guidelines are given for the rule of mixture. Different approaches are also there. This kind of research is also carried by micro mechanical analysis. Various scientists have given their contribution. In general, this rule of mixture is used, and which model we should prefer, so that models, for that also we can use the different micromechanical approaches. So likewise, if we use the modeling technique, and with the help of modeling technique, if we identify the strength, and that strength if we validate with the help of experimental method, then it is possible to have to check that what are the significant properties we expect, and what are the available properties to the experimental conditions which we have identified. At the same time, one more important aspect in case of composite material manufacture is to ensure, because for any material, whenever that material is manufactured, theoretically what kind of properties should be there, so that can be identified with the help of this modeling technique. But for experimental analysis, the most important part is to identify, to have the microstructural study, because unless and until we cannot carry this microstructural study, we can't ensure that proper the mixing of this reinforcement material has been happened inside the matrix or not. So for that purpose, the microstructure of the composite material, that is studied by using binocular, by using trinocular, by using scanning electron microscopy, by using XRD techniques also. because whatever all these physical methods which are used, maybe transmission electron microscopy, scanning electron microscopy, X-ray diffraction methodology, all these physical methods are in general used for different materials in order to ensure that whatever experiment we have carried and whatever the material we have manufactured, whether that manufactured material is as per the our requirement or not, and whether it fulfills the desired characteristics or not. So for that purpose, these are the ways. And in general, in kind, whenever we are interested in structural application, in tribological applications, then in order to ensure the proper characteristics of the materials, this scanning electron microscopy is done, transmission electron microscopies are carried, then X-ray diffraction methods are also done, and based on that, the proper material manufacturing is ensured. At the same time, the simple technique is that binocular and trinocular is the simple techniques. So in case of binocular, only by eye inspection we use. For trinocular, we use this particular composition. We observe that if the particular reinforcement has properly mixed inside the matrix material or not, whether this particular reinforcement present inside the matrix material are properly distributed or uniform distribution of reinforcement particle inside the matrix material. So that is you studied under the microscopic study only. Because if this coagulation of this reinforcement material has been happened inside the matrix, then in microstructural study it definitely observes. And if such a material has been manufactured, then this will not give the suitable material properties. So for that purpose, this microstructural study is very, very important in order to ensure the proper amalgamation or proper mixing of this particular reinforcement material inside the matrix material. Then this sample, as usual, whatever we use the metallurgical processes, all the metallurgical processes we use, same kind of processes we are using here in order to study this binocular or trinocular properties. And under the metallurgical microscopes, we observe. So we can observe here these different kind of properties which can be tested with the help of labs. So for validation, we have three kind of validation. Either we can go for the experimental analysis, we go for the modeling technique, and we can go for the microstructural studies. As far as concerned with in present investigations, as reinforcement percent increases, its yield strength was increased up to 8%, but later on this yield strength was not improved, and that may be the reason that proper wettability has not been observed. But up to 8% successfully, this alumina which is added inside the aluminum matrix composites and yield strengths are increased up to expected level. At the same time, for ultimate tensile strength, for compression strength, that is also observed. As far as concerned with the elongation, as reinforcement percentage increases, elongation always decreases. So these are some of the tests. In case of bending test, it was carried. So here we can see the comparison of modeling and experimental techniques. A small variation is always observed in case of this modeling and experimental, because modelings are always considered to be a ideal conditions, but for experimental analysis there are always certain limitations. So always there is certain difference, and that is for 20% difference that is tolerable in case of modeling and experimental analysis. So these are some of the results and discussions. Here we can observe that based on whatever the content we have added inside this one, what kind of results we observe. So if anybody is interested in tensile, she can observe the tensile strength. If anybody is interested in bending, what are the bending properties can be ensured. If anybody is interested in tribological or wear resistance applications, so that can be studied. So these are some of the microstructural analysis, and here if we can observe, so these are considered to be grains. if you see, these are the secondary dendrite arm spacing, and these are some of the grains. If that grains are smaller, then definitely that properties are improved type of properties. And if the secondary dendrite arm spacing, based on that, the properties of the material which we can decide. So these are observed under the 100x. So here we can see this is the way to represent the results and discussion. So what is the silicon modification, what is the porosity, what is the secondary dendrite arm spacing, what is the grain size. So based on that, the properties of the composite materials that are ensured, unless and until this grain size are not up to the mark, the properties will not improve. At the same time, these are some of the microstructural parameters which are studied here. And based on that, this validation process is carried. Particularly, this stir casting method, which is used in this present investigation, or liquid processing route, which is used in this particular process. So, this is successfully used in order to manufacture the aluminum matrix composite, and distribution of this alumina or Al2O3 particles are observed. We can have different reinforcement and different matrix also. Stir casting process used is the cost effective method, and it is conventional type of method. So for manufacturing this conventional method, we can continue. Materials having isotropic nature are observed, means whatever the manufactured materials are there, all the materials are isotropic in nature. Then we can have the flexibility of manufacturing based on the different parameters, and what are the influencing parameters inside that: stirring speed, time, preheat temperature, mold preheat temperature, reinforcement, size, feed rate, belt pouring rate. These are very important parameters which are used here. So in case of tensile strength, we can have proper validation with experimental and modeling techniques. For bending also, we can have this validation. For microstructural study also, the porosities are observed, then cluster is checked, because cluster formation happens, then that affects on the properties. So these are in general works in case of the stir casting processes are carried here. In this field, there is a large scope in coming days also, because which we consider here. Here we can have. Well, this is the concluding part, that there is nothing noble about being superior, so which is applicable for material also, because superiority of the material will go on increasing with previous material to next material, and novel materials is the requirement of the technology. So which is applicable for every mankind, which is applicable for metals and materials also. So nothing noble about being superior to another, but true nobility lies in superior to the previous one. So that is applicable for materials also. Thank you very much for your kind attention and giving me a opportunity to present my work here. Thanks for the organizing committee, and if any inconvenience happened due to this internet, which was not present in between, I apologize for that. Thank you very much, sir.
Thank you very much, sir. So now session is open for the question answer. Participants, please ask your question. Chelar sir, allow the participants to unmute their mic. Yes, anybody?
Am I audible?
Yes, sir. Please.
Okay, thank you, Dr. S. Patil, sir. Thank you, Dr. S. J. Madki, sir, for giving us this wonderful opportunity to attend this ATAL FDP. Dr. Sonan Kulkarni, thank you for the wonderful presentation about the composite material testing.
Thank you, sir.
Yes, very nice presentation, sir.
Thank you, sir.
Sir, I have one question.
Yes, sir.
Is the same procedure we can follow for the non-metallic composite materials also, like example soil clay, mud, sand, all
Uh,
type.
as far as concerned with this soil, mud, clay, all these categories are the ceramic type of materials.
Yeah, minerals.
Yes, sir. So, what we can do, we have three possible mixtures. In polymers, we can add the ceramics. In metals, also we can add the ceramics. So, if we use the proper polymer and ceramic composition, maybe in terms of different what we studied in metal, we added the fly ash because ash is also one kind of oxide.
Yeah,
So,
yes.
aluminum oxide or silicon oxide that is present in the fly ash. So that can be added inside the metal also, and that can be added inside the polymer also.
As a
So
reinforcement. Okay.
yes, sir, as a reinforcement
Yes,
material.
yes, sir.
So
Okay.
this kind of study we can do for the polymers also and for the metals also. Definitely, sir.
Yes, sir. Yes. Thank you, sir.
Thank you, sir. Thank you very much.
Yes, anyone else? So it was nice to hear last 1.5 hour. Dr. Kulkarni has presented very nice information regarding the AMMC. Thank you very much, sir. Anyone is having questions, doubts? Please ask. Otherwise, we'll conclude the session. And all participants are hereby informed that the feedback link will be sent on WhatsApp group. Don't worry about that. And you can fill it by tomorrow also. So I will post the feedback link in the WhatsApp group. So herewith, I will take the opportunity to thank Dr. Sonam Kulkarni for the nice presentation out of his busy schedule. He has agreed 11th hour adjustment in the session because his session was previously scheduled tomorrow, but due to some technical problem of today's speaker, so he has accepted our invitation and presented today. So thank you very much, sir. On the behalf of Siddheshwar Devasthan, our principal and all the participants and organizing committee, I thank you very much and hope our collaboration and the whatever the PPT is given to you have shared. I hope you will give to Madki sir, and we will post it in the WhatsApp group for the information of all the participants. So thank you very much. And if anyone is not having any doubts or questions, I declare the session is over here.
Thank you. Thank you very much, sir. Thank you.
Thank you, Sonan sir, and thank you all the participants. So good night, everyone. Let us meet tomorrow.
Avinash sir.
Let us meet tomorrow once again at sharp 6 o'clock. Join 10 minutes before for the third day, session number 5. Thank you.
Avinash sir. Hello.
Yes, yes, sir.
Sir, you sent previous day link, attendance
Yes,
link.
yes, yes. That will be made changes, and tomorrow or late night, evening today, the WhatsApp group. In the WhatsApp group, we will send the new link. Don't worry
Today's
about it.
link. Today's
Yeah,
link, huh?
don't worry, don't worry.
Okay, sir. Thank you.
Okay. Thank you very much.
Okay.
Sanan sir, shall I close the meeting?